Hello everyone. Last week we have covered how scalar product operation is carried out between vectors, and we defined the scalar product as the modulus of the vector A times the modulus of vector B times the cosine of the angle between those two vectors. If you multiply those three, you in fact you carry out the scalar product operation, and those were the rules for um, calculating scalar products of unit vectors. And you can actually you can see, you don't have to memorize these products. You can find out which one was equal to 1 and which one was equal to 0. For example, when you multiply I and I, the angle between them is 0. Therefore, cosine 0 is equals 1 is equal to 1. And then you get 1 when you multiply the unit vectors of the same kind. And lastly, even though you are multiplying two different vectors, at the end you'll get a non-vector, a scalar, at the end of the scalar product operation. And today we are going to use this operation to calculate work. In the last video, we defined the work as force times distance. But here we are only dealing with the force component parallel to the displacement, the distance, the movement actually. Therefore, there is a cosine theta over here to calculate that component in the direction of the movement of the force. So this is familiar from the last slide, and this operation is actually the scalar product operation, which can be defined like this. So let's take a look at this quick example. We have a particle which is moving in xy plane, and that particle undergoes a displacement delta r, given like this, and it is under effect of a constant force like this. In part A, the question asks us to calculate the magnitude of the force and the displacements of the particle. So you know how to calculate the amplitude of a vector. Therefore, from those values here, 5i and 2j, and here 2i and 3j, we obtain the amplitudes of the force and the displacement as this. In part B, we are to calculate the work done by the force F on that particle. So the only thing we need to do is to substitute the force vector and the displacement vector into the work equation. Force was defined as 5i plus 2j, and the displacement delta r was defined as 2i plus 3j. Okay, then all we need to do is some simple mathematical manipulation. We have to distribute the force on delta r like this. 5 times 2i here, 5 times 3, 5i times 3j here, and 2j times 2i, and 2j times 3j. So from the previous slides, we know that if you multiply same kind of unit vectors, you will get 1. Therefore, 5 times 2 is equal to 10, and I times I is equal to 1. Therefore, here we obtain 10. Then after calculating all the terms one by one, you'll get 16 joules as the work done by that force. In the previous example, the force that is doing work on the particle was constant. So if the force is varying with respect to time or the position of the particle that is being affected by that force, what should we do? We are going to use calculus to calculate that work, and that work done by that force. Simply, we are going to integrate the force over the interval of the displacement. So then the area, therefore the area under the force distance curve will be equal to the work done by that force. And mathematically, we know that we can calculate that work done using this definitive integral. Another simple example to comprehend the concept further. Here we have a force distance curve defined as this. A particle or an object is moving from point A to B, then point B to C. During this travel of that particle, the force acting on the particle is changing. First, the force is constant, then it's changing linearly from 4 meters to 6 meters. And to calculate the work needed, work done by the force, we need to calculate the area under the force distance curve. I'm not gonna go all over them, but you will get 25 joules of work here by that force. The work done by a spring on an object or on a particle is equal to force times distance as well. But here we know that the force applied by the spring is equal to minus k, the spring constant, times the x, the total elongation or compression, amount of compression of the spring. Since in this example spring is moving on the x direction, in order to represent the force in vector form, we need to put a I unit vector here. And take a look at this force distance curve. When the spring is at its most compressed position, the force applied by the spring is at its largest value. But when as it gets closer to the neutral position, to x is equal to 0, the force applied by that spring will decrease. And since the relation between the force and the elongation, or the amount of compression of the spring, is linearly correlated with the constant k, we have a straight force distance line. And during this travel of the object, here this orange block, again we can calculate the work done by that spring on the block by calculating the area under the force distance curve, which will be equal to 1 over 2 k times x squared. So let's calculate the work done by spring on the block. Okay, the spring force was defined as minus kx, and then to put that force into vector form, we have put a little I here. And since the force is changing with respect to displacement, force is varying with respect to displacement. Therefore, we need to use the integral form of the work equation. Here we have spring force, and here we have differential R instead of delta R, because this displacement is the differential amount of displacement. Then when we substitute the force term here, minus kx I, scalar delta x I, then putting the integral boundaries. Initially the spring was at minus x max, then it travels to 0, the natural position of the spring, and if you calculate this integral, you'll get 1 over 2 k x squared x max squared. This term is identical with the first one we have calculated in the previous slides. Let me show you here. Here, the work done by a spring is expressed in a more general way. This subscript S that designates the spring, the work sub S. And let's consider the spring is moving from initial position to final position instead of a maximum position to 0. Here, in the general description, the spring is moving the initial position to the final position. And after calculating this integral with this integral boundaries, we will obtain 1 over 2k times x sub I squared minus 1 over 2k times x sub f squared. And this is the most general form of the work done by a spring. Be careful, by a spring. And try to keep this definition in your mind. And here, let's take the same example from the from a forces point of view. Let's say we have a force that is compressing the spring in the minus negative x direction, and the direction of that force is obviously in the negative x direction. This time spring is resisting to that force, but their magnitudes are equal, but their directions are opposite. So this time the force is doing work on the spring. Previous slide, the work was done by a spring, but here in this slide, in this example, the work is done on the spring. So in order to calculate the work done by the applied force, we need to calculate again f scalar delta dr, and we can calculate the magnitude of this f sub applied. We know that the magnitudes of those two vectors are equal. The directions are directions are opposite. Okay, to calculate the work done on the spring, we have to take the scalar product of the force and dr. The resistance force applied by spring was equal to minus kx. If we remove this negative sign here, we obtain the applied force, the magnitude of applied force. Therefore, this is why we don't have any minus sign here. And again, the displacement is differential in the integral, and we have two I terms, I unit vectors here, because the displacement and the force is lying on the x axis. And initially, the block was at x maximum position, x initial is equal to minus x max, and then we allow block to move right while applying a force on it. Then when the spring reaches to its neutral position, which is at x is equal to 0, we obtain the work done on the spring as minus 1 over 2k x max squared. Let's go back to the previous slide to compare those two results. Don't forget we have a minus sign here, but we don't have a minus sign over here. The amount of work is the same, but depending on your point of view, the sign of the work done or the work can differ. Please be careful. So read carefully. And again, in order to write the work done on the spring in a more general way, we can calculate this integral. This time we don't have any minus sign here, therefore the final 1 over 2k x sub final and the second term 1 over 2k x sub initial squared will switch places. Okay, let's talk about kinetic energy. To express the work in a more general way, we can modify the integral form of the work equation with including all the possible forces that are acting on the object or the particle. And it is very possible that there can be several forces acting on the object. Therefore, instead of writing one single F, the one single force, we write total sum of the forces acting on the object. And consider this block example again. Let's say it has a mass of m and its acceleration is a and constant. So the total sum of the forces acting on that acting on that block has to be equal to m times a. We know that from our Newton's laws of motion studies. And this is the total sum of the forces, and this differential x is the distance traveled by that block. And to calculate this integral, we need to do some math. So instead of writing a, we can write dv over dt, and using the chain rule, we can, instead of writing dv over dt, we can write dv over dx and dx over dt and dx, and those dx's will cancel out, and the whole equation will be equal to the initial equation. But we are doing this manipulation to be able to calculate the kinetic energy in terms of the velocity. So here this term is equal to velocity, and those dx's will cancel out, and we will end up with m times velocity times dv, right here. So from if we choose the integral boundaries as the initial velocity to final velocity, we will obtain the net work on the block as this. Be careful, we have 1 over m times velocity squared minus the initial velocity squared, 1 over 2 times m initial velocity squared. Okay, now I want you to pay attention here. This net work is is due to the change in the velocity from the final and between the final and the initial positions. In other words, we can say if you change the velocity of an object or a particle, you will do work on that system depending on the magnitude, the sign of the change of the velocity. If the velocity is the only thing that is changing, then we can calculate the net work done by the system or done on the system simply by the calculating the difference between two states of the system, two kinetic energies at the two states of the system. Let me put it that in a more convenient or in a more tidy way. When work is done on the system and the only change in the system is in its speed, the net work done on the system is equal to change in the kinetic energy of the system. This is what I was trying to say in the previous slide. So what about potential energy? Um, Consider this physics book and say we are a force F is pulling the book upward from initial position to final position. And initially, book was standing still at that height, y sub I, and at the final position, again the book is standing still. Therefore, there are no velocity changes of the system. Uh, so therefore, there must be another type of energy, since we applied force on the system, but the velocity stayed constant between two states. Therefore, we have to have another form of energy, which is the potential energy. And in this example, this potential energy is due to gravitational acceleration, gravitational force. And while applying force to the book, we overcome the gravitational force in order to raise the book from initial position to final position. So let's try to calculate the net work again done against the gravitational force. Here our classic work equation: applied force times no, not times, applied force scalar delta R. And we know that the magnitude of the applied force should be equal to m times g, and since it is in the vertical direction, we need to put the unit vector j, and scalar the amount of displacement y final minus y initial, again times j, again with unit vector j. And if you make the calculations, you'll have mgy final minus mgy initial. But generally speaking, the gravitational potential energy is equal to the current y coordinate of any object, any particle, times the mass of the object or particle times the gravitational acceleration. And difference between two different states of the potential energy of two different states is the network done on the system or by the system. The second type of potential energy is the elastic potential energy. Some objects like spring or like a sponge uh, can store energy, can store mechanical energy when you compress them or when you try to elongate them. And this stored energy in elastic substances is called the elastic potential energy. And it can be calculated using 1 over 2k x squared. Here the x designates the amount of compression or elongation of that elastic substance. Okay, let's talk about conservative or non-conservative forces. But before explaining what are those things, let me give you two examples. The gravitational force is conservative, whereas the friction force is non-conservative. And to explain, how can you tell whether a force is conservative or non-conservative? You should check the path dependence of the force. For example, the friction force is dependent on the path of the object, path followed by that object. Since if an object following a longer path, the work done by the friction force will be larger, right? But for gravitational force, the amount of the length of the trajectory is not important. The only thing is important is the amount of displacement in the vertical direction. Think of an object sliding on an inclined surface. For gravitational force, the work done by gravitational force is only dependent in the displacement in the y-axis. Or let me give you another example. If you move an object on an horizontal plane, pure horizontal plane, no matter how long is the path of travel, the work done by the gravitational force will be zero, because you are not changing the height of the object. So just for looking those two examples, we can deduce those two statements. The work done by a conservative force on a particle moving between any 2 points is independent of the path that taken by that particle. And the work done by a conservative force on a particle moving through any closed path is zero. Think of that book example in the two previous slides. Let's say we raise the book to a higher point, then we lowered the book at the same point which the book was at its initially. The total work done by the gravitational force will be zero, because in the final and the initial, between the final and the initial states, there are no changes in the height of the book. Finally, again with this book example, if this book in the example will follow the orange path, of course the work done by the friction force will be larger than the blue path. Always recall this example when you have difficulties to remember what was the conservative and the non-conservative forces. So, since the friction force or the work done by the friction is dependent on the path, the length of the path, the friction force is non-conservative. But the gravitational force is conservative because it is independent from the long length of the path. Let's continue with the conservation of energy. When you isolate a system from its surroundings, in other words, if you can stop any work interaction between a system and its boundaries, the total mechanical energy of the system will remain constant. And for an isolated system, change in the mechanical energy will be zero. Is zero all the time if you can isolate the system. Of course, in real life this is not possible, but when we are modeling systems as engineers, we can assume that the system is isolated from its surroundings. Let's take a look at this ball example in order to explain conservation of energy. Initially, ball is at a vertical position of h, and the potential energy of the ball is equal to m times g times h. Since initially the ball was held by the ball is held at a constant height, the kinetic energy of the ball is zero. After releasing the ball travels in the negative direction, downward. Its potential energy will decrease, of course, and the kinetic energy will increase. But the total sum of those two quantities will be always the same. In other words, the change in the total mechanical energy of the system will be zero. This is how you express this things mathematically. Another very important term in engineering or in physics is power. Power is defined as the change in the energy with respect to time, or time rate of change of energy of a system. And it has a unit of joule per second, and this joule per second, since at the denominator we have joules and the denominator we have seconds, dt, this joule over second has a special name called watt, which was named after James Watt. So 1 watt is equal to 1 joules per second, and if you make the necessary conversions in order to convert the joule per second to SI unit system, you will have 1 kilogram per meter squared over seconds cubed. Another often used unit of power is horsepower. 1 horsepower is equal to 146 watts, and HP, 1 horsepower, is mostly used in United States and United Kingdom. There's another thing that I want to mention. So please do not mix up the power and the work or the energy. And power and energy are two different things. Power designates the time rate of change of the energy, the change in the energy per unit time. And here we have an example of energy unit, 1 kilowatts hour, and it is equal to 3.60 times 10 to the power 6 joules of energy. This is not power, this is energy. And to calculate power, we need to, since we are looking for the change of the system in a unit time, we need to differentiate the work done on the system or by the system with respect to time change in the time, differential time. So we know that the work done on the system is equal to force times distance, and if we differentiate this scalar product with respect to time, we will obtain f scalar velocity. Take this example. And an elevator is being pulled by a motor, and let's quickly write the force balance equation in the vertical direction. And from looking the free body diagram of the elevator, the tension on the cord is directed upward, and the friction force is directed to downward, and m times g is due to gravitational acceleration and the mass of the elevator. And after writing the force balance equation, we will obtain the tension on the cord as F plus m times g, which will result. Yeah, I know that I did not provide the numerical values before and the example, but here this example is just to demonstrate the power concept. Okay, and the tension on the cord is 2.16 times 10 to the power 4 newtons, and in order to calculate the power to move that elevator cabin to upward, we need to multiply the force with, we need to take the scalar product of the force and the velocity. Since the tension and the velocity vectors are directed in the same direction, and the angle between them is 0. And remember, scalar product means that the amplitude of the first vector times the amplitude of the second vector times the cosine of the angle between them. Since the angle between them is 0, cosine theta or cosine angle between those two will be equal to 1, then, and therefore we have t times v. And then if you multiply those two parameters, you will get the power required to raise the elevator upward with that velocity. Also, if you change the velocity required, for example, let's say if you want to raise the elevator with a speed lower than 3 meters per second, you will require a lesser amount of power, of course. So do not forget, the power is always depending on the time rate of change of things. Okay, that's all for this video. This week I wanted to change the way of online lecturing. Instead of flawless short videos, I wanted to present real-time lessons, real-time lectures. So see you in the next video.